Okay, so finishing 4.2, jumping around. Example 4 says to evaluate the integral from 0 to 4 of dos equis. Um, that's how Hank would read it, right? With respect to x, by expressing it, the definite integral geometrically. Okay, so remember the thing that you're taking the integral of is called the what? Integrand. Good. And if we could sketch that, like f of x equals 2x, we can interpret any integral geometrically. Now, that from algebra 1 is the line with the slope of 2 everywhere that passes through the origin. Okay, so this one is asking us to integrate from x equals 0. So here's your left end point, and I'll just call this x equals 4. Now the dx, you can think of dx as being not just with respect to x, but with respect to the x-axis. With respect to the x-axis. Are you okay with the WRT? Have you all seen that before? With respect to, with respect to. So this would be the region we're looking for. Now, because we're going from left to right, from 0 to 4, and my y values on that interval are positive, the integral is going to give us a positive number. Okay. And so it has two meanings in that sense. The first meaning in general would be the area of this region would tell us how much we accumulated if we were accumulating at this rate, 2x, on this time interval from 0 to 4. The magnitude of the area, which is always positive, will tell us how much we gained over that time period. But because it is entirely above the x-axis and we are going from left to right, it also, the integral will also give us the area. So in this case, how do we find it? Well, it's just a triangle, right? It's a right triangle. So we know that the integral from 0 to 4 of 2x dx is just the area of a triangle, which is 1/2 the base times the height. 1/2 the base times the height. So what is the base from 0 to 4? Well, it's 4 minus 0, yeah? And what's the height? Well, it's just the function value at 4. Yeah, and you could figure that out. You can actually label it. This is 4 units tall, and this is 4 times 2, that's 8. So you could just plug it in and say, oh, that's 4 times 8. And now you just simplify. Half of 8 is 4 times 4, it's 16. All right. Elementary. Elementary. So again, let's interpret it two ways. If you wanted to paint this triangle, you would go to Sherwin-Williams or whatever, and you'd say, I need enough paint to cover 16 square feet. Okay. And they give you whatever the paint is to cover it once, twice, whatever. But let's say that you had units. Let's say that f of x is measuring the rate of something in gallons per hour. It can be a rate equation, even though it doesn't have a prime on it, right? Because remember, little f is the derivative of big F. So let's say that the y values were measuring in gallons per hour, and the x-axis was time in hours. Well, when you find area, you're multiplying y values times x values. What would the units be if we were to multiply the units of the y-axis times the units of the x-axis? What would the units be? It would be gallons, right? So this number could also tell us then from 0 hours to 4 hours, we accumulated 16 gallons. If we were collecting gallons at a rate of 2x gallons per hour. Okay, so that's what that means. You can always figure out the units of the integral by multiplying. Y values times x values. Gallons per hour times hours is gallons. You can always figure out the derivative or the units of the derivative by dividing, right? The units of the derivative would be gallons per hour, or gallons per hour squared. Okay, so very important. The derivative is division. We want to try and make a connection between the two. So that would be gallons per hour. Okay, but the integral, which is the antiderivative, is multiplication. And that would be gallons per hour times hours, which of course is just gallons. And I guess we can simplify this too. Gallons per hour squared. All right. Very, very important. So how are division and multiplication related? They're inverses of each other, right? They undo each other. Guess how the derivative and the integral are related? They're inverses of each other. Yeah. Okay. Now, the whole point of this section is to realize that you can use the definite integral to find area, but you can also use area to find the definite integral. You just have to know which one you're looking for. And then you have to know where are the y values positive, where they're negative. Okay. Because the definite integral, we'll just write this here, the definite integral from a to b of f of x dx always gives you the net accumulation. It's a vector. So if we had some negative values, it would cancel out. For instance, let's just piggyback on this problem here. What if I wanted to integrate now from, let's say, -2 to 4 of 2x dx? Well, we can come over here now and add that to it. Okay, let's say here's -2, and now it's with respect to x. So we have a region now that's below, bless you. It's below. Now here's the deal. If I find the area of that region as a positive number, a magnitude, I can use that number to help me find the integral. And vice versa. If I wanted to find the area and I integrated it from -2 to 0, I would get a negative number, but then I just know that the magnitude would give me the area. So let's go ahead and find the area of this little region. The area of this little region is going to be 1/2 the base times the height, base times height. So what is the base? It's 2 units, right? And then what is the height? It's 4 units. So notice I'm not assigning that as a negative value or I'm just assigning them as magnitudes. And so that would be 1/2 4 times 2, which is 4. So if you went to Sherwin-Williams now, or wherever your paint store is, and you wanted to paint both of those triangles, you would need enough paint to cover. Let me go ahead and do this. I'm going to write the 4 in there and circle it. And I'm going to write the, what was it, 16? I'm going to write the 16 in there and circle it. This is typically what we do. When we find the areas of regions, we do them off to the side on our workbench and we write the magnitude in there and circle it. Okay. So now if I wanted to paint that, and we're talking about square feet, how many square feet do I need paint for? 20, right? Pretty easy, right? 4 here, 16 there. I need enough to cover 20 square feet. That's the area. And again, I found that geometrically. But if I wanted to figure out over here, what is the integral from -2 to 4, it's not equal to 20 because 20 assumes that everything's positive. So first of all, am I going from left to right or right to left? Left to right, from 2. It's always from 2. So this is left to right. That's important because now everything is going to be as it seems. Negative y values, negative accumulation. Positive y values, positive accumulation. So what would the accumulation be from -2 to 0? -4, right? -4. That's where I assign it the number. So this is -4 plus 16, which equals what? 12, right? So very, very different. Now, what would be a scenario for something like this? You can't dismiss negative values out of hand because a negative value can kind of go back in time. I think I mentioned like the guy on these examples here, a guy was like gambling, right? Losing, gaining money. So that could be the scenario here. For this 2-hour period from -2 to 0, he lost $4, right? But then over the next 4 hours, he got $16 back. And so what was his net accumulation at the end of that, 6-hour period? 12. He came out 12 ahead, right? That's what the definite integral always gives us. It gives us the net accumulation. All right, what would this be? What would be the integral from 4 to -2 of 2xb? It would be -12, right? Because now it's going backwards from right to left. And so now if you were to actually write it out below there, you would say, okay, from 4 to 0, the area is 16. And normally it's positive, but we're going backwards. So it's negative 16. And then from 0 to negative 2, the area is 4. And normally it's negative, but it's going to be positive. So we get negative 12. Okay. So we can use area to help us find integrals. And we can also use integrals to help us find area. Let's look at that. What we just did is we found the areas and we used them to calculate the definite integral. But let's say I wanted to set up a definite integral that would give me the area. 4, 6, and 14. Oh, that's not a date. I remember. Okay, let's come over here. Let's say that we go into Sherwin-Williams, like I need to cover 20 square feet. And he's like, show me your calculations. I want to see how you did that. Okay, I'm going to take the integral from negative 2 to 0 of 2x dx. But if I just calculate that, what type of number is that going to be? That's a negative number. Can we have negative area? No. So how can I make this definite integral positive? Same magnitude, opposite sign. Very good. There's two ways to do it. You can either, since I've written this down, you can either just put a negative in front, right? That'll calculate the integral and then change the sign. Or the other way to do it is to just flip the intervals of integration, go from 0 to negative 2. And if we have a preference, ooh, that's not a good color. I would say develop a preference for this one. Because when we start setting up integrals and you have a negative term, you know how that can sometimes be, right? Sometimes you don't distribute. So if you can get rid of the negative and make everything positive, that works. So either one of those, and then all I have to do is integrate on the rest of the interval from 0 to 4 of 2x dx, which is going to give me a positive number, 16. Do I want it to be positive? Am I trying to find area? Yeah, so I don't need to modify it at all. Okay, so I could do the same thing up here. So these are the calculations you would show the guy at Sherwin-Williams, and he was just like, dude, I was just kidding about that. I don't even know what calculus is, but I'm glad you do, right? No. These guys are smart guys. Yeah. Like I've got a doctor's in mixology, right? Yeah, doctorate in mixology. Okay, so what did I do different? The only difference is this. In the first term, I'm either putting a negative out front from negative 2 to 0 to make the negative integral positive, or in the top one, there is no negative out front. What did I do? I just flipped the intervals of integration. So instead of going from negative 2 to 0, I go from 0 to negative 2. Right. Both of these are going to come out to be 20, 20. Yeah. Yes. All I'm trying to do is get you to realize two things. The definite integral and the area, are they the same thing? No. Can they be the same thing? Yes. When is the definite integral and area the same thing? If we go from left to right and all of our y values are positive. That's it. That's it. Okay. Are they closely related to each other though? Yes. If you can find areas of regions using geometry, or maybe sometimes they're given to you, you can assign your own values of plus or minus to them to evaluate a definite integral, depending on whether you're going from left to right or right to left, or whether they're above or below. But you can also use the definite integral, which is what we did here, to help you find area. Now, why is this going to be important? We're not always going to have the graph. You might be given an equation and it's going to say, find the area of the region. You're just going to have to know, okay, the graph is negative from negative 2 to 0, and it's positive from 0 to 4. So I can integrate from negative 2 to 0, but that's going to give me a negative number. And I want to fix that. So I'll either change it by putting the sign out front, or I flip the intervals of integration. Okay, that's it. Area can help us find integrals, and integrals can help us find area, but they're not the same. Okay, so that was number 4 with a little bit of extra on it. And then number 6. Use your calculator to find the area of the region. Okay, so if you want to grab your calculator, e to the x minus 3, the x-axis and the vertical line. So you will be asked to find area. How do we know we're trying to find the area here? It actually says the word area. So now when you read that word, you're on positive alert, positive alert, positive alert. And whose job then is it to make sure that everything is positive? It's yours, right? Now, before we go to the calculator, let's just kind of review. This is a transformation of our parent function e to the x, right? What does the -3 do to this in any graph? Down 3, 1, 2, 3. So the horizontal asymptote, which used to be at y equals 0, is now at -3. And let's see, what is the y-intercept? What is f of 0? -2. Boom, like that, okay? So it's going to be increasing, and it's going to cross somewhere like that. I want to find the area of the region. Now, when it tells you to find area, it's going to give you like the borders, because it has to be like contained. So what does it say? It's bounded by the graph itself, the x-axis, so I'm going to draw that in red, and the vertical lines x equals 0, that's the y-axis, and x equals 3. Now, where's the vertical line x equals 3 in relation to the x-intercept? Is it to the left or to the right? I think it's to the right, but how can I be sure? Well, let's see where the function crosses the x-axis. Let's set it equal to 0. Right? This is how we find x-intercepts. Y-intercepts, we plug in a 0 for x. X-intercepts, we have to set the whole thing equal to 0. And I haven't picked up the calculator yet because I don't want to. I want to review. Now, how do I un-e something? What do I do to both sides? Natural log it. So if you natural log the left side, you got to do it on the right side, and it goes in front. And now you get x equals the natural log of 3. What is bigger, x equals 3 or the natural log of 3? X equals 3. Yeah. Okay. This is less than 3. So I know that this x-intercept right here, which is the natural log of 3, is kind of in between the intervals of integration. So I have this region, which is below, and then I have this region, which is above. If I were just to integrate straight across from 0, I put x equals -3. This is x equals 0, right? If I just integrated from 0 to 3 of the function parentheses e to the x minus 3 dx, is that going to give me the area of those two regions? No, it's going to be some negative quantity plus some positive quantity, which will not be the area. Okay, so I have two options here. I can either manually set up an integral that'll give me the area, but that requires me to know where the graph is positive and where it's negative. Do we know that? We do. We just did a little bit of work. So let's go ahead and set it up. So the area is going to equal to, and again, if I just integrate straight across from 0 to the natural log of 3, it's going to give me a negative number. I want to find the area. So how do I make that negative number positive? Good. From ln of 3 to 0. And now I could just do of e to the x minus 3 dx. That's going to be positive. And then plus, now I can cruise from the natural log of 3 to 3 of e to the x minus 3. So this is the example where we're using the definite integral to help us find the area. And notice how I closed off the integral. Let me talk about that because this is a perfect time to mention it. On the AP exam, if you have just a single integral and you accidentally leave off the dx, they don't take off normally because it does. They're like, but they won't take off. But what if I left off this one in the middle?
Rip up the paper, they screaming.
Something to that effect. Yeah, because now you're not closing off the first integral and you're saying that whole next term is you're taking the integral of an integral. So, so that one you would lose points. So just remember that the integral has bookends. It has a left bookend and a right bookend, and you don't want books falling off the shelf. Okay. Let's go ahead and type that into the calculator. I bet we're going to get a number. I hope we're going to get a number. Now, here's what we could do. If this were a calculator problem, we could certainly do what we just did. There's nothing against that. It took a little bit of time, but rather than type in e to the x minus 3 twice, I'm just going to type it into y1. Second ln to the x power, click to the right, minus 3. Boom. Now, I don't care what the graph looks like because I already graphed it by hand. I just want to use y1 as a place to access the equation. So now I'm going to go to the home screen. Second mode, flush. Boom. Now I got to type this in. You always have it written on your paper/iPad before you go to the calculator. How do we get the definite integral? Math 9, right? Math 8 is the integral. Math 9 is not just the INT, it's the most extreme type of INT. F in INT. See that? That means function integral. So math 8 is the derivative, math 9 is the integral. You can also get it by hitting alpha window. If you go to alpha window, there's your absolute value, but look at number 3 and 4. That's just another place to get them. But that's like extra keystrokes. So I like math 9. Now we'll just type it in. Let's do the first integral. The natural log of 3, close parentheses, click up to 0. And then I can either type in e to the x minus 3 or recall it from y1. Recall it. Alpha trace. I messed that up. Hang on. Alpha trace, number 1, and then dx. Now, don't hit enter. Don't hit enter. We got plus, okay? Plus, this is why we do it from the home screen. We don't care to watch it shade. Math 9, now we go from the natural log of 3, close parentheses, to 3, oh no, of alpha trace number 1, dx. Now, y'all's is probably a little different than mine. You can still see the whole thing, which is nice. Mine gets cut off the screen. I hit enter and I get 12 point, and here's where we round or truncate, 677. And that would be square units. And we would get full credit if this were a calculator question. All right. Now, if this were a non-calculator question, we would have to do this way, and then we would manually find the antiderivative. Just for kicks and giggles, what would the antiderivative, which is the same as the indefinite integral? How do I know this is an indefinite integral, not a definite integral? There's no thingamajiggermabobbers thingies, right? There's no intervals of integration. So this is just the antiderivative. What would be the antiderivative of e to the x? E to the x minus, what's the antiderivative of 3? 3x, good, and then plus c, okay? And then as I showed y'all when I was here last, then you could just, if you wanted to, you could then evaluate it. So it would be a lot of work, but let's go back to, hey, this really was a calculator question, and it really did just want the area. We don't have to spend all this time deciding where it's positive and where it's negative, because there's an easy way to make it entirely positive. If you do the absolute value of f of x, remember that transformation reflects everything that's negative across the x-axis. And if it's already on the positive side of the x-axis, it stays the same. I could just nuke it, as I like to say, make it all positive, and then I can integrate straight across from 0 to 3. Let's see if it works, okay? Or I could say the area is equal to the integral straight across from 0 to 3 of the absolute value of e to the x minus 3 dx. Now, I wouldn't want to do that if I had to do it by hand. You know why? When you put the absolute values around that, you kind of hamstring yourself. It's not the same antiderivative as the one we just found. The absolute values mess it up. But on a calculator, it's like, calculator doesn't care. It's doing it numerically anyway. So here I go. Math 9. And then I'm going from 0 to 3. Now, how do I nuke it? Where do I get the absolute value? There's 2 places. You can either hit math number 1, because it is, right? Math, click to the right, and there it is, ABS. Or you can go to the shortcut that I just showed y'all, alpha window. F2 has some of the more commonly used ones, and it's the first one. So it doesn't matter. And now you can either type in e to the x minus 3, or as I'm going to do, I'm going to recall it from y1. And now with respect to x. If you write this on your paper, let's say this is a calculator question, and you write that on your paper with the absolute values, that's indicating your method. We're like, That's awesome. And now if I hit enter, I should get the same, right? Yeah. It is different. Why is it different?
Oh, no.
The calculator is getting two different numbers, and that's just because it's calculating it two different ways, but they are supposed to be equivalent, right? That's a flaw in the programming. That's rounding error. But look to 3 decimals, is it the same?
Yes.
Yeah. And so that's one of the reasons why College Board requires 3 decimal accuracy, because for the most part, your calculators, whether it does it one way or the other, it's going to be the same answer to 3 decimals, maybe even more, right? Here we got to 5 decimals. So there you go. Do you get extra credit on a calculator question by splitting it up into 2 integrals and manually making the negative positive? No, you don't. So that's why strategies are important, right? Am I allowed to use the calculator? Am I not? If you are finding the area of the region on the calculator, just do it this way. Take the absolute value of your function and just go straight across. If the function happens to already be entirely positive, it's not going to hurt anything, right? Yeah. If you have to do it without a calculator, then you have to manually set it up, okay? So in this case, we're using the integral to help us find the area. Whereas over here, when we found the areas geometrically, we then assigned them positive or negative values. We were using area to find the integral. So far, so good. It's a hugely important idea. Look at Ethan living up to his name. Yeah. See, they shouldn't have taken a picture of you that was posed. They should have just hung out here.
We offered our camera roll.
Yeah. Did you? Oh, yeah. There you go. There you go. All right. So 4, 6, and 14. 14. Oh, yeah. Okay. So this one is, for lack of a better place to put this one, I just threw this one at the end because it's kind of playful. So we don't need the calculator for that. All right. So if the antiderivative or the definite integral from 0 to 2 of sine of x dx equals 2, use this fact and the symmetry of sine of x to find the following. Now, before we do that, let's go ahead and get a preview of coming attractions. As I mentioned to you in the next section, there's going to be a way to evaluate a definite integral without having to do Riemann sums, but it all requires us to be able to find the antiderivative of the integrand. Do we know what the antiderivative of sine is? Yes, it's what? Negative cosine of x. And we know that's right because we can take the derivative of that and get sine. Now, when it's a definite integral, as I told you the other day, absolutely, yes. You don't even need to use the plus c because it's going to cancel. So what we do then is we put this evaluation bar on the back end, and we read that as evaluated from 0 to pi. Now, the fundamental theorem of calculus says this. This is the fundamental theorem of calculus. It's in the next section. But now that I know what the antiderivative is, I don't need the plus c. It's going to cancel. I can evaluate it by plugging in the top and then subtract it from plugging in the bottom. Okay, so we read it from 0 to pi, but we evaluate it from top to bottom. So that's going to be negative cosine of pi minus negative cosine of 0. Top minus bottom. Top minus bottom. And now let's evaluate it. What is cosine of pi? Ooh.
Oh, it's
Negative 1. Good. Times the negative 1 that's in front of it makes that positive 1. Minus cosine of 0 is 1 times the negative that's in front makes it that. And now we have 1 minus negative 1, which is 1 plus 1, which is what? 2. Yeah. So does that check out? Does that scan, as they say? Yeah, that scans. That's not sus at all. Right? Okay. So now we know it's true. Now here's what we know. We know that for the lobes of sine and cosine, both of them, they're equal in area above and below. We also know that each of the lobes, if you will, have a line of bilateral symmetry. So we can actually partition it and say this area is 1 and this area is 1. Yeah. And that would be what? From 0 to pi. So basically, for every quarter cycle for a sine or a cosine, we know that the area is 1. Okay. Now, let's see then what would be the definite integral for sine of x from pi to 2 pi. Well, Sahala, there's Sahala. Here's pi. Here's 2 pi. Would it be 2? It's -2. Because we're going from left to right. And where does it live, above or below? It's below. When your y values are negative, your accumulation is going to be negative. It makes sense, right? In chronological order. Now, if you go backwards, it's like watching a video in reverse. You don't see the guy throw up, right? You see the guy suck up all the vomit. You're like, how does that happen? Yeah. Okay, good. Yeah, you're welcome. Yeah, that'll stick. All right, what's the integral from 0 to 2 pi? Well, there's Sahala. Here's 0. Here's 2 pi. Yeah, it's 0 because we're finding the definite integral. This area is 2. This area is 2. But from left to right, it's 2 minus 2, which is 0. There it is. We use areas to find integrals in this case. All right, the integral from pi to pi halves. Well, let's see. Here's Sahala. Pi is here. Pi halves is here. Ah, sweet. Good. We know the area of that lobe is 1, but we're going left to right. So everything is backwards. So this is -1. Whoa, that guy wants in. I'm sorry, right to left. Yeah, right to left. My bad. Right to left. It's backwards. It's backwards. So the y values that are positive are now negative. Okay. All right. How about this one? 0 to pi of 2 plus sine of x. Well, you can anti-differentiate both of them separately, but we want to use what we know about this. So let's think about standard transformation form. If I were just to add 2 to any function like this on the back end, what would that do to any function graphically? Shifts it up 2, right? So if you think of Sahala, let's think of Sahala. Draw Sahala nicely. Sahala. And then just grab it and move it up 2. There's 1. There's 2, right? So here is the old x-axis right here. But now, if I've moved it up 2, this right here is 1, this is 2, and this is 3, right? So what used to oscillate between -1 and 1 now oscillates between 1 and 3. So if you were to draw this right here from 0 to pi, here's pi right here. What have you done? Well, you're taking everything that used to be there, right? This had an area of 2, and you're basically just propping it up with the rectangular platform, aren't you? Yeah, and it's pi units wide by 2 units tall. So what would the area be? 2 pi. Okay, so this should be 2 plus the platform, 2 pi. Okay, vertical shift. Now, because we did get the preview of coming attractions, let's use the fundamental theorem of calculus that we technically don't know yet. When it's multiple terms, if you can find the antiderivative of each term, you can use the FTOC. What would be the antiderivative of 2? 2x. We already know the antiderivative of sine is negative cosine. We don't need the plus c because it's a definite integral. It's going to cancel. So now we go on the back end from 0 to pi. Plug in the top minus plug in the bottom. You'll see me do this all the time, especially when I have multiple terms. I put receptacles there because that negative in the middle, it can derail some people. So when I plug in the top now, I get 2 pi minus cosine of pi. When I plug in the bottom, I get 0 minus cosine of 0. And oh, by the way, if this were a free response, could we stop there? Yeah, that's a numeric. Sure is. But let's verify it. This gives us 2 pi minus cosine of pi. What is cosine of pi? We should probably evaluate it. -1. Cosine of pi is -1 times the -1 that's there makes it +1. And now if I distribute, I get -0. And then I get plus cosine of 0, which is 1. If I add all that up, that's 2 pi plus what? 2. Is that the same as 2 plus 2 pi? It is. It is. All right. All right. How about this one? 2 sine of x from 0 to pi. Well, let's go ahead and graph Sahala. Here's Sahala. It goes from 1 to -1. What would multiplying it by 2 do? Stretch it how? Vertically. Yeah. So if the gray area here is 2, what would the purple area be? Is that intuitive? Ah, very good. The question that I have is the area twice as big? Geometrically, there's no real indication why it should be twice as big. But because we can pull constant multiples out front, right? You get in the back of the truck, which is really the front of the integral, right? Now, you could say, okay, it's 2 times, and then this, of course, is 2. So it does equal 4. It did double. The area doubled. Okay, so those properties are nice. All right, let's look at this guy. What does replacing x with x minus 2 do to any function? It moves it right 2 units, 1, 2. So what used to be at 0 is now at 0 plus 2. And what used to be at pi is now at pi plus 2. And what used to be at 2 pi is now at 2 pi plus 2. What would be the integral then from 2 to pi plus 2? It's just 2. I'm integrating the same region. It's just over a different interval, right? In other words, I shifted everything right too, not just the graph, but I shifted the intervals of integration right as well. And notice that they're opposite, right? This kind of gets people sometimes. In the function, it's x minus 2, and we know that means to the right. And that's why it's pi plus 2. We have to add it. It's opposite. Okay. I don't think we're going to finish. We have less than a minute left, but maybe we could do the rest of these for a warm-up tomorrow. Okay. So if you want to submit your notes tomorrow after the warm-up, you can. The worksheet, remember, is bonus. There are 6 questions. Okay. And it combines 4.1 and 4.2. And then those are going to be due tomorrow by 4:30 p.m. And then tomorrow we're gonna hit the ground running again. We're gonna move on to the next section after we warm up with these last 3. So, but I hope you understand now, integral and area, not the same, but closely related. Any questions? All right, have a great lunch. Good to see everybody again. I missed y'all yesterday.